Welcome back to our today's lesson, and today we are going to derive the Clapeyron's equation of three moments, or in other words what we call three-moment theorem. And in this case we have four diagrams on our board. The first diagram showing a continuous beam, the second diagram showing bending moment diagram due to vertical rods, the third diagram showing bending moment diagram due to support moments, and the fourth diagram is the resultant bending moment diagram. That means the combination of these two bending moment diagrams. Now, the Clapeyron's equation of the moments is used when we want to plot the bending moment diagrams for a continuous beam. Now, a continuous beam is a beam which is supported on more than two supports. For example, our beam here is a continuous beam since it is supported on three supports. Now, this theorem states that when we want to get the value of the support moment, that is moment at A, which is this MA, moment at B, as well as moment at C, we are going to use this formula, MA L1 plus 2MB into L1 plus L2 plus MC L2 being equal to 6A1 bar X1 all over L1 plus 6A2 bar X2 all over L2. So that is how this theorem, the moment of three moment, that is the three moment theorem states, and therefore this is the formula we want to derive. So ladies and gentlemen, join me as we derive the three moment theorem, or the Clapeyron's equation of three moments. And we are going to begin with considering span A and B. Therefore, consider span A, B. Now, on span AB, we have L1, that is the span between support A as well as B. Now, in this case, we are going to begin by this. Let Mx be the bending moment due to vertical loads at a distance x, from the end A, and Mx prime, let it be the bending moment due to support moments, at a distance x, from the end A. So that's what we are going to have. Now, the net bending moment is going to be the net bending moment will be, now remember in structures 2 we have a topic known as slope and deflection, and when we are talking about deflection we usually use this EI d squared y over dx squared. This one is going to be equal to mx minus mx prime. So this is the net bending moment. Remember, when you talk about net, then subtraction have to come in, and therefore that's why we are saying that the net bending moment will be mx, which is the bending moment due to vertical loads at a distance x from A, minus mx prime, bending moment due to support moments at a distance x from A. Now, from there, we are going to multiply both sides by x. or we are going to multiply through by x, because when we multiply moment times distance, we usually get what we call moment of area. And therefore, multiplying through by x, multiplying through by x, we are going to get what? Multiplying through by x, we get, therefore this is going to be ei multiplied by x d squared y over dx squared, which is going to be equal to x mx minus x mx prime. Now, after multiplying through by x, the next thing will be integrating. Therefore, integrating so we are going to integrate from the limits 0 to L1. Therefore, integrating from the limits 0 to L1. And remember, when we integrate the above equation from 0 to L1, we are talking about the span A to B, where we have L1. So the origin is 0 all the way up to B, L1. Now, when we integrate this equation, this is how we are going to write it. So, integration from 0 to L1 of ei x d squared y over dx squared dx, that's how integration is usually written, is equals to integration from 0 to L1 of x mx xmx dx minus integration from 0 to L1 of x mx prime dx. Now, this one is going to lead us to ei, and remember, E is the modulus of elasticity, I is the moment of inertia. Combination of the two, E multiplied by I, gives us what we call flexural rigidity. And therefore, this is going to lead us to ei into x dy dx, and this one is at B, minus y. Here we have 0 and we have L1 above, being equal to, now x multiplied by mx, we have said that when you multiply moment multiplied by distance, we shall get what we call moment of area. And therefore, this is going to be A1 bar x1, whereby A1 is the area of this bending moment diagram due to vertical rods. Bar x1 is the distance of the center of gravity from, that is all the way up to A. The distance from the center of gravity of this bending moment diagram due to vertical rods between span A and B all the way to A. So that's is going to be minus, this one is going to be A1 prime bar x1 prime, whereby A1 prime is the area of this bending moment diagram between span A and B due to support moments. Bar x1 is the distance from the center of gravity of this bending moment diagram, if the center of gravity is there, all the way to A, that is bar x1 prime, bar x1 prime. So that's how it's gonna be. Now, from there, we are going to solving the left hand side of equation 1. So let's call this equation 1. Now when we solve the left hand side, that is this side of the equal sign, we are going to have this EI, that is the fractional rigidity, into this x, we are going to replace it with L1. Therefore, this is going to be L1 dy dx. And remember, dy dx, that is known as slope. And this is at b, minus yb, whereby y represent deflection. So we have slope at b minus deflection at b. Minus ei into this x again, we replace it with this 0. Remember, you have a 0 here. So that x being substituted with a 0, dy dx. This one now is at a, that is the slope at a. This one is the slope at b minus deflection at b. This one is slope at a minus deflection at a, that is ya. So that's what we are going to have. Good. So solving that equation further is going to lead us to what? To the following. So we are going to have ei into L1 dy dx at b. We have said that is the slope at b, and we know that slope is usually denoted by that symbol. So slope at b minus deflection at b, that is yb, minus ei into, here we have 0 times dy dx at a, definitely that's going to be 0. So we are going to remain with minus ya, which in this case is deflection at support a. Now we know very well that deflection at the supports is usually equal to 0, and therefore deflection at a as well as deflection at b are equal to 0. That is deflection at the support a as well as deflection at the support b. And therefore our equation is going to be ei L1 multiplied by slope at b. So yb and ya are zeros, making the whole of that to be 0. So we are done with solving the left hand side, so that we are going to equate to these, that is a1 bar x1 minus a1 prime bar x1 prime. Let's call this equation 2. Now from there we have said this a1 prime is the area of this bending moment diagram between span A and B due to support moments. And therefore, let's first of all solve this part, that is A1 prime. So A1 prime, when we look at this shape here, the shape ABKJ, we find that that is a trapezium, and therefore A1 prime will be the area of this figure, which is a trapezium between span A and B. And therefore we know very well that area of a trapezium is given by a half into A plus B, and in this case A is MA, B is MB, multiplied by the height. The height of this shape, this trapezium, is going to be L1, that is the span between A and B, multiplied by L1. Good. Bar x1 prime will be given by this, and this coming from a topic that is known as centroids and moment of inertia. That is structures module 1. So if you have forgotten, please remember to go back there. By x is usually given by summation of ax all over summation of a. And summation of ax, when we now expound it, usually is a1 multiplied by x1 plus a2 multiplied by x2 plus so many other figures an multiplied by xn all over a1 plus a2 plus the area of so many other figures all the way to an. In this case, we have a trapezium here, and for us to be able to get bar x1 prime, we are going to divide this trapezium into two shapes, whereby the first one will be a rectangle, the other one will be a triangle. So let me sketch it here so that we can visibly see what we are talking about. So our diagram is like that, whereby this end is MA, that is bending moment at A. On this other end we have MB, bending moment at B, and here we have L1, the span between A and B. So we are going to divide it into two, whereby we are going to have a rectangle and a triangle. Now let's call this figure 1 and this one figure 2. Therefore A1 is going to be the area of this rectangle, which is going to be MA multiplied by L1. So the area of figure 1, that is MA L1. It's x, that is the distance from the center of gravity of this triangle all the way to the end A, is going to be half AB, of half the breadth of this rectangle, and that's going to be L1 divided by 2. Therefore A1 x1, when we now multiply these two, we are going to have MA L1 multiplied by L1 over 2. So we are done with the first diagram. The second diagram is a triangle, and therefore A2 is going to be a half multiplied by the height or the base. Let's start with the base, multiplied by the base. The base is L1, a half L1 multiplied by its height, the height of this triangle, and the height of this triangle will be given by MB minus MA. That will be its height. So MB minus MA. X2, that is the distance from the center of gravity of this triangle all the way up to A. Remember, from the 90 degrees angle, that is from this corner, the right angled corner, all the way to the center of gravity of a triangle, that's usually given by a third of the base of that triangle. The remaining part from the center of gravity to this corner, to this acute angle of this triangle, that will be given by the remaining fraction, which is 2/3 of the base. And therefore x2 is going to be 2/3 of the base of this triangle, which is L1. Therefore A2 x2 is going to be multiplying these two, that is the area A2 times x2, and is going to be a half L1 into MB minus MA multiplied by 2/3 of L1. Therefore that is the value of A2 x2. Very good. Good. So that's what we have as a1 x bar, a1 x1 and a2 x2. Now we have said that bar x1 prime will be given by a1 x1 plus a2 x2 all over a1 plus a2. So this is going to be a1 x1. We have it as ma l1 over 2 plus a2 x2. We have it as a half of L1 into MB minus MA 2 over 3 L1 all over A1 is MA L1, that is the area of the triangle, the rectangular section, so that is MA L1 plus A2 is up to this point, a half of L1 into MB minus, sorry, this is MA, MB minus MA. Now from there we are going to factor out L1 since L1 is common in both equations. So this is x1 prime by x1 prime. So by x1 prime will be given by factoring out L1. This is going to read us to MA L1 over 2 plus a half, this L1 goes outside there, a half of MB minus MA multiplied by 2/3 of L1, that L1 remains, all over, factoring out L1 on the denominator part, we are going to have L1 into MA plus a half of MB minus MA. That's what we are going to have. Now, these two and this one are going to cancel out, and therefore here we are going to have this and that and L1 there. So that's what we are going to have. This L1 and this one are going to cancel out. Now, on the numerator, when we add the two fractions, we are going to have the LCM of 2 and 3 being 6. Therefore, the LCM is 6. So here we are going to have 6 divided by 2, that is 3. And that's going to be 3 multiplied by MAL1 plus 6 divided by 3, that is 2. Therefore, this is going to be 2. Let's bring L1 here. 2L1 into MB minus MA. So that is solving the numerator. Solving the denominator, we have 1 and 2. The LCM is going to be 2. So this is what we are going to have. 2 divided by 1, that is 2. And therefore that's going to be 2MA plus 2 divided by 2, that is 1. That's going to be MB minus MA. This will lead us to 3 MAL1 plus 2L1 into MB minus MA all over 6. We multiply that by the reciprocal of this denominator, this equation as the denominator, which is going to be 2 over 2MA minus MA, that is MA. Therefore, over MA plus MB. by 2, 1 by 2, 3. And this will lead us to the following. So we are going to have 3MAL1 plus, let me write this 3 somewhere there, plus 2L1 MB minus MA all over this 3 multiplied by MA and B. That's going to be 3 into MA plus MB. So that is bar x1 prime. We are still going on very well. The next thing we are going to do is to factor out L1. And when we factor out L1, we are going to have this L1. We can say L1 over this 3, therefore L1 over 3 multiplied by the numerator we have 3MA plus, we open the brackets, this is going to be 2MB minus 2MA all over MA plus MB. This will lead us to L1 over 3 multiplied by 3MA minus 2MA. That's going to be MA, 1MA, and therefore we are going to have MA plus 2MB all over MA plus MB. So that is it, and this is bar x1 prime, So let's call this equation 3. Now from there we are going to substitute the values of a1 and x1 into this equation, equation 2. So we have bar x1 here, and we had the value of bar, that is a1 prime. This is bar x1 prime. A1 prime, we say that it is the area of this trapezium, which was a half into MA plus MB multiplied by L1. That is what we had. Therefore, solving the values of equation 3.1 into A1 x bar 1, we are going to have this EI multiplied by L1 multiplied by slope at B being equal to A1 x1 minus A1 prime, which is a half of MA plus MB multiplied by L1 times x, that is bar x1 prime, times bar x1 prime. Bar x1 prime is this third equation, which in this case is, let me write it here. So we have times this equation times L1 over 3 into MA plus 2MB all over MA plus MB. Let me solve whatever is on the right hand side first. So we are going to have this. I am going to leave whatever we have on the left hand side. I'll come to fix it later. So we are going to have A1 x1 minus L1 over 2. L1, bringing it here, L1 over 2 into MA plus MB multiplied by L1 over 3 into MA plus 2MB all over MA plus MB. Very good. So what will happen is that this MA plus MB and this MA plus MB are going to cancel out, and we are going to remain with this A1 x1 minus L1 times L1, that is L1 squared, all over 2 times 3, that is 6. So you are going to have 6 there, into MA plus 2MB. So that's what we are going to have. And remember, on the left hand side of the equal sign, let me squeeze it here, we have EI L1 slope at B. That's what we have. Now from there, we are going to multiply through by 6. And therefore, when we multiply through by 6, we are going to have 6 EI L1 slope at B being equal to 6 A1 x1 minus L1 squared into MA plus 2MB. Then we divide everything here by L1. So when we divide everything by L1, we are going to have 6EI slope at B. This L1 will cancel out definitely, being equal to 6A1 x1 all over L1 minus 1 L1 will cancel with that is L1 will cancel with 1 L1 here, and we are going to remain with only L1 into MA plus 2MB. Let's call this equation 4. That is our equation 4. Now, when we consider span BC, remember, all these we were considering span AB. When we consider span BC, therefore, considering the span BC. So when you consider the span BC, we are going to have the following. It is going to be 6EI into bracket negative slope at B. Why negative slope at B? Because the distance x from A to B and the distance x from C to B are in the opposite direction, and therefore the slope at B on the span AB and the slope at B on the span CB, since they are acting in the opposite direction and they are vector quantities, they are going to have different signs. This one positive, the other one negative. So that's going to be equal to 6. So instead of A1, we are going to have A2. Instead of x1, x2. Instead of L1, L2. Minus L2 again here into, instead of MA, we are going to have MC minus, that is a plus 2MB. MB is going to remain the same. So this is going to be our equation 5. Our equation 5. Yep. So guys, as we had down here, we had equation 4 as well as equation 5. So the next thing we are going to do, we are going to add these two equations. And let's begin with adding the left hand side. So when we add the left hand side, we are going to have this 6EI slope at B plus 6EI negative slope at B. which is going to be 6ei slope at B minus 6ei slope at B, which is going to be 0. So on the left hand side, we are going to have 0. Adding the values of the right hand side, we are going to have 0 on the left hand side being equal to 6a1 by x1 over L1, let's collect the right terms, plus this one, 6a2 by x2 all over L2 minus this one here, L1. Let's open the brackets. So when we open the brackets here, we are going to have the minus MA L1 minus 2MB L1. We come back here, this is going to be minus MCL2 minus MCL2 minus 2MBL2. So that's what we are going to have on the right hand side. Now we have this one and this one here. So this is going to lead us to 0 being equal to 6a1 by x1 all over L1 plus 6a2 by x2 all over L2 minus minus MAL1 minus, we can factor out 2MB here. So this is going to be 2MB into L1 minus times minus, that is plus L2, and then minus MCL2. Finally, we are going to bring these values with negatives on the left hand side of the equal sign, whereby the negative signs are going to change to positive. And we are going to have MAL1 plus 2MB into L1 plus L2 plus MCL2 being equal to 6a1 by x1 all over L1 plus 6a2 by x2 all over L2. And therefore, ladies and gentlemen, this is now what we call the Clapeyron's equation of 3 moments, or the 3-moment equation. So thank you very much, ladies and gentlemen, for watching our video. If you have liked it, please consider subscribing to our channel. Also, don't forget to hit the notification bell so that whenever we upload a new video, you will be the first person to be notified. Thank you very much. Let's meet in yet another lesson.